This video is on unimolecular nucleophilic substitution, also known as SN1. Picture this reaction: an acetate, a stable anion, reacting with a tert-butyl chloride. Well, at first you'd say, well, SN2 can't happen because it's a tertiary carbon, but turns out the reaction occurs anyway to form this ester and to form chloride anions. Well, it's tertiary carbons, therefore it cannot be SN2, yet a substitution is occurring and it must be something else. Well, if we investigate this reaction further through experimentation, we can find out that the rate does not match that of SN2. The rate in fact equals reactant constant times the concentration of only the tert-butyl chloride. i.e., the rate only depends on the concentration of the electrophile. It is independent of the concentration of nucleophile. No matter how much we increase the concentration of the nucleophile, the reaction rate will not increase. Therefore, as it's only dependent on one molecule, we refer to this reaction as unimolecular nucleophilic substitution, or SN1. As the nucleophile is still present in the product, the reaction must occur in multiple steps where the rate determining step does not involve the nucleophile. This means that this reaction must occur in multiple steps, or at least in two. The first with just the electrophile losing the leaving group. This must be the rate determining step. And once we have formed this carbocation, the nucleophile can attack it to give us our final product. The energy profile of this reaction is different to the SN2 reactions, as instead of going through a single transition state, we actually form a stable carbocation reactive intermediate. So there is a pause in this reaction, and there are two separate transition states, one before the reactive intermediate when a bond is being broken, and a second transition state after the reactive intermediate when a bond is being formed. The energy levels of the starting materials and products will still determine if the reaction is exothermic or endothermic. So as the formation of the carbocation is the rate determining step, the stability of the carbocation is the most important factor. That means that this reaction will occur the fastest or the highest rate on tertiary carbons, followed by secondary carbons, finally primary carbons. Yet, if we look into it, there are no SN1 reactions on methyl groups or primary carbons. We can see a nice correlation between the structure of our electrophile and the relative rate of the reaction. As you'll notice, tertiary carbons clearly have a much faster rate of reaction than secondary carbons, and as we increase the resonance, such as in this tertiary carbon with each carbon having resonance, we see that the rate of reaction is extremely high. So it makes sense that resonance stabilizes the carbocation, because that's what resonance does. It just redistributes that positive charge. However, how come more substitution stabilizes it? Well, more substitution allows for more hyperconjugation, which was when a bond donates electrons to the cation directly. And therefore, the more bonds around a carbocation, the more stable it's going to be. So what about the stereochemistry of SN1 reactions? Well, as we know, a carbocation is formed. So our intermediate is an sp2 carbon with an MTP orbital. What does this mean? It means we have a trigonal planar intermediate, meaning a nucleophile can attack from either side with equal opportunity. If the chiral center is the site of SN1 substitution, it means that a carbocation is still going to be formed, and that carbocation is going to be trigonal planar. This leads to a 50-50 mix of products, or in other words, racemization, or the formation of a racemic mixture. So you give it a go. Draw the products of these two reactions. You may pause now. And here are the answers.